Okay, let's go ahead and get started. For those of you who are watching live, you go ahead and type in your name and the days and times your class meets, so you get credit for being here. And if you're watching the recording, I'm going to ask that you just quote something from the video and then also put in your name and the days and times the class meets as a reply to the video, and then that way you'll get credit as well. All right, we're talking about special factoring patterns today. Before we actually do any factoring, we just need to start recognizing the patterns and the names of the patterns. So the first one, which I'm hoping many of you are already familiar with, is a difference of squares. And what that looks like is a polynomial, a binomial, specifically two terms, that fits a pattern of something squared. I'm going to call that something A just to give it a name, minus something else squared. Okay, so what we're going to do is I'm going to list some binomials and we're going to figure out if they fit that pattern or not. So first we're just getting accustomed to identifying the pattern. So which of these fit the pattern? Okay, so the first one is the binomial x squared minus 9. So the first thing you want to look for to see if it fits this pattern is if it has two terms. Is it a binomial? Yes, it is. That's the only way it can be a difference of squares, is that it has two terms being subtracted. And then each of these two terms must be a perfect square. Now, in order to determine if it fits the pattern, if each term is a perfect square, you need to figure out if there's something that you could identify as your A and your B, the thing being squared in each term. So for example, in this one, the first term is x squared. The x is being squared. And in the second term, the 9, you can think of 9 as 3 squared. So in the second term, the thing that's being squared is a 3. Or another way of saying this is we can identify our A and our B. So we're going to do that in each case, identify the A and the B from the special pattern. So in this case, I identified that the A is x and the B is 3. Those are the things being squared. So this does fit the pattern of a difference of squares. Yes, and I'm going to call that difference of squares, DOS. Fits that pattern. Okay, let's look at another one. So for this one, we have x squared minus 9x. Okay, again, the first thing we look for is to see if it's a difference of, if it's a binomial, if it's two terms, and then if it's subtraction, if it's a difference. So we do have two terms being subtracted, and then we want to think about, can we write each of these terms as something squared? All right, so here we still have x squared, so we already know that's something squared. But what about the 9x? We know 9 can be written as 3 squared. But we have a little bit of a problem here because I have to end up with an x somehow. And if I put an x in here for part of my thing that's being squared, my b, if you square 3x squared, you get 3 squared x squared, or 9x squared, not 9x. This is not a perfect square, this x, so it doesn't fit the pattern. There's no way we can figure out a b that's going to be squared to give us 9x. So that means that no, it does not fit the pattern. That doesn't mean, by the way, that you can't factor it. When we look at factoring later, there's other techniques, but it doesn't fit the difference of squares, so we won't be able to factor it like a difference of squares. All right, how about x squared plus 9? So in this case, we have two terms, but they're not being subtracted. So we don't even have to worry about trying to find an A or a B. This pattern, the difference is referring to subtraction. So if we don't have subtraction, then we don't have a difference of squares. All right. How about x squared plus 6x plus 9? So right away, we count the number of terms. This is not a binomial. It's got 3 terms. Terms are things separated by a plus or minus. Difference of squares is always 2 terms being subtracted. We have 3 terms being added, so definitely not a difference of squares. How about 9x squared minus 1? Okay, so our first thing we check is the number of terms. We have 2 terms being subtracted, so far so good. And now what we want to think about is, can we write each of those terms as something squared? Can we find an A and a B that fits the pattern? So in this case, 9 is 3 squared, and then x squared is a perfect square. So we could think of this as 3x quantity squared. Squaring each part would get us back to what we started with, so that would work. What about the 1? Well, a 1 could be thought of as 1 squared, because when you square 1, you still get 1. So actually, we could use our A could be 3x, and our B could be 1. So yes, it does fit the pattern of a difference of squares. Okay, how about, let's do a couple more here. How about if we had 4 minus y squared? So again, we look and we see, do we have a binomial, 2 terms? Yes. Are they being subtracted? Yes. So far so good. And then we want to look and see, can we think of something, a number that we can square to get 4? Yes, absolutely. 4 is 2 squared. Y squared is obviously y squared. So each of these is a perfect square. So this is a difference of squares. And in particular, the A in this case is referring to 2, and the B in this case is referring to y. So yes, this is a difference of squares. Okay, let's do a couple more. I'm going to write these in blue just so you can see that they're different ones. All right, so let's look at 9x to the 4th minus y squared. Okay, is it a difference of squares? Well, we have 2 terms and they're being subtracted, so far so good. Is 9 a perfect square? Yes, 9 can be thought of as 3 squared. Is x to the 4th a perfect square? So you might think no, but actually, isn't it true that if you square x squared, you get x to the 4th? So x to the 4th is actually a perfect square. So we could write this term, oops, my eraser doesn't want to work here. Let's see, there we go. So this first term, 9x to the 4th, could be thought of as, 3x squared squared. And what's being subtracted from it is obviously a perfect squared. It's y squared. So we just identified our A is 3x squared, and our B is y, the thing being squared. And so yes, it is a difference of squares. In fact, anytime you see an even power, that can be written as a quantity squared. Okay, so one more. What if I had x to the 6th minus 4y to the 6th? Is that fitting the pattern of a difference of squares? So a difference of squares has to be 2 terms being subtracted, and you have to be able to write each one as a quantity squared. X to the 6th, notice it's an even power. So what power of x could you raise then to the 2nd power in order to get x to the 6th? Well, Remember, when you raise a power to a power, you actually multiply the exponents. So whatever is going here has to be multiplied by 2 to give you 6. So that would be 3, right? So this would be x cubed squared. So this is a perfect square. And over here, 2 squared would give you 4, and y cubed would give you, if you square it, y to the 6th. So yes, we just figured out that to fit the pattern, the thing being squared in the first term is x cubed, so a is x cubed. The thing being squared in the second term is 2y cubed, so b is 2y cubed. And yes, this is fitting the pattern of a difference of squares. All right. Now we're going to practice factoring a difference of squares later. Right now, I want to look at a couple of other patterns and see if we can identify those as well. Before I move on, I'm just going to check on the technical stuff here. Please, if anyone notices a technical issue, please let me know. Uh-oh, I see a problem. So hopefully I've fixed that now. Let's see. Okay, that's weird because I had the settings over here. Okay, so now let's talk about a difference and sum of cubes. So we already said that we have a difference of squares is a special pattern that we need to be able to recognize, where you have something squared, like x squared minus y squared. But we always use a squared minus b squared just to represent the pattern. And we're going to look at some other patterns as well. We're going to look at the difference of two cubes. Cubes means power of 3. So that would mean we would have a cubed minus b cubed. Something cubed minus something cubed. And another pattern we're going to want to be able to factor later is a sum of cubes. And so the sum of cubes is going to look like a cubed plus b cubed. Something to the third power plus something to the third power. So what we're going to do now is we're going to try to identify whether we have one of these patterns rather. So we're going to identify the pattern of a difference of squares, a difference of cubes, or a sum of cubes, or none of these. And if it is one of the patterns, then we want to also state what our A is equal to and what our B is equal to. Okay? Okay, again, the reason we're doing this is because we're going to be able to factor things that fit these patterns in a special way, but we're not factoring yet. First, we're just going to learn to identify the patterns. So I am going to first start with the polynomial y cubed plus 27. Okay, so notice that these three patterns that we're looking at right now are all binomials. They all have two terms. And this guy has two terms, so far so good. It might fit one of the patterns. We have two patterns with subtraction, the difference of squares and the difference of cubes, and one with addition. So the only way this one could fit one of these patterns is if it fits the sum of cubes. So let's see if it does. The way that we determine if it fits the sum of cubes is, can we think of each of these terms as something to the third power? In this case, we know y is being raised to the third power in the first term, so we're good to go there. But what about 27? Can 27 be thought of as something to the third power? Yes, it is a power of 3 to the third power. 3 times 3 is 9, times 3 is 27. So we see that we have found an a of y, right? The first thing that's being cubed in the first term is y, and the b for the pattern is 3. So this does fit a pattern. It fits the sum of cubes, which I'm going to abbreviate SOC, sum of cubes, yes. Okay, let's look at another one. All right, the next polynomial, which we're going to look at, is x cubed minus 8. So again, these three special patterns that we're looking at are all binomials. This is a binomial, so that's good. 2 of them involve a difference or subtraction. So if it fits one of these patterns, it's going to have to either be a difference of squares or a difference of cubes. Hello, Sandro and Daniel. I'm glad that you were able to get in. I'm sorry if there was a technical problem earlier, but I think you'll be able to pick up where we are now. We're looking at the patterns difference of squares, difference of cubes, and sum of cubes, and we're just trying to identify which polynomials fit those patterns. So the one we're looking at right now, x cubed minus 8, it's definitely a binomial, which is good. It's a difference, so we're either looking for a difference of squares or a difference of cubes. And we have to figure out then if we have 2 terms that are something squared or something cubed. Well, x is clearly cubed, so that's not going to fit difference of squares. Let's see if it fits into difference of cubes. So the first term is something cubed for sure. Is 8 something cubed? So 2 times 2 is 4, times 2 is 8. So yeah, 8 is 2 to the third power. So now that we see that this is a difference of 2 things that are third powers, we know that we are fitting the pattern of a difference of cubes, where the a in the pattern, the base of the first term that's being raised to the third power, is x, and the b in the pattern is 2, the thing being cubed in the second term. So yes, this fits the difference of cubes. I'm going to abbreviate that DOC. Yes, it does. And a is x and b is 2. Okay, let's look at another polynomial. All right, so the next one we're going to look at is 4x squared minus 36. 4x squared minus 36. Oh, actually, let me change that one. I don't like that one for a reason that will be clearer later. Let's do 4x squared minus 81. Okay, so again, it's a binomial, so it could possibly be one of these 3 patterns. It's a difference, so it's either the difference of squares or the difference of cubes. We know that because it's subtraction. Now we just need to figure out if it could be, if each term can be written as a perfect square, perfect cube, or neither. The x squared is a hint, right, that it's a difference of squares, but we have to be able to write the whole term as a perfect square. So in this case, 4 is also a perfect square. It's 2 squared. So we could write this term as 2x quantity squared, and that would give us our 4x squared. How about 81? Is it a perfect square? Yeah, it definitely is. It's 9 squared. Okay, so what we have here is, to fit the pattern of a squared minus b squared, we would think of a as being 2x, and we would think of b as being 9. All right, so this definitely is a difference of squares. Yes. And why is that important? Because we're going to see later that we can factor very easily if we know we have a difference of squares or a sum or difference of cubes. Okay, let's look at another polynomial. 4x squared plus 36. All right, so once again, we see that it has two terms, so it's possible it could fit one of these patterns, but it's a sum of two terms. So the only pattern that we have that is nice and factorable is a sum of cubes. Notice there is no sum of squares. And unfortunately, this guy contains squares and not cubes. So what we have here is actually called a sum of squares, and it doesn't factor, so it's not a pattern that we're interested in. So I'm just going to say no. It does not fit any of these patterns. And next, let's look at 8y cubed minus 27z cubed. 8y cubed minus 27z cubed. Okay. So binomial, two terms. Subtraction, so either difference of squares or difference of cubes. We see that the variables have powers of 3, so if anything it fits the difference of cubes, but we have to make sure that we can write the whole term as something to the third power. So for example here, is 8 a perfect cube? Yes. 2 to the third power is 8, and y cubed is a perfect cube. So we could think of this first term as 2y, oops, I wrote squared, 2y cubed. How about the second term? Well, 27 is 3 cubed, so we could think of this second term as 3z cubed. So the answer is yes, that is it does fit the pattern of a difference of squares. If we think of A as being 2y and we think of B as being 3z, it's going to be a difference of cubes, yes. Okay, a couple more. Okay, the next one that we're going to look at is kind of tricky. X to the 6th minus y to the 6th. Okay, so in this case, we definitely have two terms, so we have a binomial. It's either going to fit a difference of cubes or a difference of squares because it's subtraction. All right, so let's start with trying to see if it can fit the pattern of a difference of squares. So x to the 6th, 6 is an even power, which always indicates that you can think of it as a perfect square. And the way you determine what's being squared is you remember that we're going to have x to some power squared. To raise a power to a power, you actually multiply the exponent. So what would you multiply by 2 to get 6? That would be the power of 3. So you could think of this first term as being x cubed squared. Okay, so it is a perfect square. The second term here we could think of as y cubed squared the same way. So if we think of the a as being x cubed and the b as being y cubed, then we have a difference of squares. All right, it fits the pattern. Okay, but I said this one's tricky because actually 6 is also a multiple of 3. So what that means whenever you have a multiple of 3 is that you can also think of it as a perfect cube. Let's see how that would work. So x to some power cubed. What power would that have to be? Well, again, 2 times 3 is 6, so that would have to be the power 2. So we could think of this as x squared cubed. That would still equal x to the 6th. We could also think of this as y squared cubed. That would still equal y to the 6th. So what does that mean? That means we have a difference of cubes as well. So we could think of a as being x squared and b as being y squared, and in that case we would have a difference of cubes. This does not happen very often that you could think of it as two different patterns, but it can happen. And so all that means is that later on when we're trying to factor some of these guys, we will have two different ways we could go about it. Okay, so hopefully you're starting to see how the difference of squares, difference of cubes, and sum of cubes work. And now what we're going to do is try and apply the factoring formulas for these patterns. Let me check on our technical stuff going on here. Oh good, we've been joined by a lot of people. I see Todd and Oleg and Kristen. I hope you guys are able to hear me. Please tell me if you see anything that's causing a problem, a technical issue that I might not be aware of. I know there was a delay. Some of you were probably not able to log in at first, so sorry about that. But hopefully we're good to go now. All right, so let's go ahead and talk about how we factor binomials. Using special factor formulas. Some binomials can be factored just by taking out a GCF, but others we use these special factoring formulas because they fit our patterns. So what patterns am I referring to? First of all, we saw difference of squares. Okay, the difference of squares looked like a squared minus b squared. And you may have learned previously that a difference of squares always factors into what I call conjugates. That means the same two terms, but with a different sign in the middle. It factors a squared minus b squared factors into a plus b times a minus b. All right. We also can factor a difference of cubes. And the way that works is if you have a cubed minus b cubed, it will always factor into a minus b times a squared plus ab plus b squared. This is a longer formula and it's probably new to the vast majority of the students in intermediate algebra. So this is a new one. Put a little star next to it that you need to memorize it. Oops. I am going to give you a little trick to help you memorize it in a minute, but right now I want to also write down the formula for factoring a sum of cubes. So the sum of cubes, we're adding two cubes, and that factors into, oh, I wanted it to be blue. Hold on. Let's make it blue here. A cubed plus b cubed factors into a plus b times a squared minus ab plus b squared. So you see the sum and difference of cubes factor very similarly. We have the a, we have the b, we have the a squared, ab, and b squared, but the signs are different. So there's a nice little mnemonic device you can use to remember the signs. So it's called SOAP, S-O-A-P, SOAP. And what it stands for is the same sign as you started with, the opposite sign that you started with, and always positive. Okay, so what I mean by that is when you go to factor something of a pattern of a cubed minus b cubed, you know that the first sign is going to be minus because it's the same as what you started with. The second sign is going to be positive because it's the opposite of what you started with. And the last sign will be positive because it's always positive. When you factor a cubed plus b cubed, your first sign will be positive because it's the same. The second sign will be negative because it's opposite. and the third sign will be always positive. So that's just a little way of remembering the signs that go there. Okay, so whatever you got to do, flashcards or whatever. I'm also going to mention the pattern of a sum of squares. Okay, unfortunately, it doesn't factor, at least not in the real number system, so it's not factorable. So when you see that you have a sum of squares, you know you're not using one of these patterns, so that's why it's important to recognize that. Okay, so let's look at some examples then. So for our first example, we're going to factor, and we have x squared minus 4. All right, so we want to see if it fits one of these patterns. As soon as you see that you're factoring a binomial, you're going to compare it to these patterns. Notice it's a difference, so it could possibly fit a difference of squares or a difference of cubes, but we see there's a perfect square on the x here. So is 4 also a perfect square is what you want to ask yourself next. And the answer is yes. You can think of this as x squared minus 2 squared. Right? So it fits the pattern of a squared minus b squared, a difference of squares, where your a is x and your b is 2. All right, so how does a squared minus b squared factor? It factors into a plus b times a minus b. Write down your formula. All right, so our polynomial, putting in x wherever you see an a and a 2 wherever you see a b, is going to be x plus 2 times x minus 2. Now students often ask me, does it have to be in that order? And the answer is no. Remember, multiplication is commutative. X minus 2 times x plus 2 means the same thing as x plus 2, x minus 2. So either of these would be correct factorizations. Also want to remind you what factor means. When we factor something, we're writing it as a product. See how it's written as a product of two unknown numbers, x plus 2 times x minus 2. Okay. All right, let's look at another one. So what if I asked you to factor, and I gave you 9x squared minus 1. So you would notice, I would expect you to notice the number of terms, in this case 2. Hope we're all doing well. Okay, good. Thank you for letting me know, Sabrina. All right, so 2 terms, so possibly one of these patterns. It's a difference, so either difference of squares, difference of cubes. The x is being squared, so that's your hint that it's a difference of squares. And so now we just need to figure out what our a and our b are. What's being squared? So 9 is 3 squared. So we can think of the first term as 3x squared. And 1 is actually also a perfect square. It's 1 squared. Okay, so what we have is a difference of squares. It fits the pattern a squared minus b squared, where a is 3x and b is 1. So write down the formula. The more times you write it, the better you'll remember it. A squared minus b squared factors into a plus b, a minus b. So our polynomial that we're factoring, wherever you see an a, you're going to have a 3x. Wherever you see a b, you're going to have a 1. So that's 3x plus 1 times 3x minus 1. Okay, so that's your final answer on that one. It's completely factored. Okay, I'm just going to check on things here. All right, looks good. Okay. Now, one thing I've kind of been glossing over and ignoring is that before you go ahead and apply one of these patterns, you really should check to see if you have a GCF that you can factor out. And in these problems I've been giving you, there haven't been any GCFs, but once you once you've done a few, we'll start to expect that you're able to deal with a GCF as well. So you want to be careful about that. So I'll show you an example real quick of one of those. Okay, so what if I asked you to factor and I gave you x cubed minus 8x. Okay, so a lot of times when students see the binomial, they're real gung-ho about matching it up to one of these patterns, and they see the third power on the x and they start trying to make it fit the a cubed minus b cubed. And that might not necessarily be the case. So it actually isn't in this case, because if you look first before trying to fit the pattern, well, first of all, if you did try to fit the pattern, yes, you have an x cubed, and in fact you have a 2 cubed, but this x here is not something cubed, so it doesn't quite fit that pattern. But before we even check if it fits the pattern, we really should factor out any common factors. And so what you'll see here is that this 2-term binomial has an x in each term in common. So we could factor an x out, and that's going to leave behind x squared minus 8. Okay, now you should check to see if that fits one of these patterns. The only possibility, since x is being squared, that is that the x squared minus 8 fits a difference of squares, but 8 is not a perfect square, so actually it doesn't, and we would just stop here. Okay, so be careful. Factor out any GCF before trying to fit one of the patterns. Okay, let's look at a couple more. So let's see. What if I asked you to try to factor and I gave you 8y cubed minus 27? Okay, so first of all, we look for a GCF, but there's nothing that goes into 8 and 27 evenly. Then we see, okay, it's 2 terms, so, and it's a difference. So could it be a difference of squares or a difference of cubes? Well, y is being cubed, so that's a hint that it's probably a difference of cubes, if anything. Is 8 a perfect cube? Yes. This is the same as 2 cubed, so 2y cubed would give us the original term back. Is 27 a perfect cube? Yes. 27 is 3 cubed. Okay, so what we see here is it fits the pattern of a cubed minus b cubed, a difference of cubes, where your a is 2y and your b is 3. So let's go ahead and write out the formula. The more times you write it, the more you'll remember it. So we have a minus b times a squared plus ab plus b squared. That was the formula up here in green. Okay, so everywhere you see an a, you're going to replace it with the 2y, and everywhere you see a b, you're going to replace it with a 3. So let's do that. All right, so first we have a minus b, so 2y minus 3. And then we have a squared, so 2y squared plus a times b, so 2y times 3 plus b squared is going to be 3 squared. Okay, so obviously we don't want to leave our answer looking like that. So coming down below here, the 2y minus 3 looks good, but we need to work this out a little bit. 2y quantity squared is going to be 4y squared plus 2y times 3 is going to be 6y plus, here we have a 9. Oops. Oh no, that's right. Okay. Let me see how we're doing here. Looks like maybe we're still good. Okay. All right. So that would be our final answer. Now, later on in class, well, actually, in some cases in your class, we've already talked about factoring trinomials. In other cases, we have not, at least not as much. So what we're going to see, though, if we try to use, if we try to use the AC method to factor this trinomial, we'll see that this is actually a prime polynomial. It does not factor any further. That is always the case with these formulas for the sum and difference of cubes. So you don't ever need to try and go and factor that trinomial further. Okay, which is good. So that means we're done. All right, so that's how you would factor a difference of cubes. Let's look at another one. My PowerPoint is going crazy. Okay. All right, so how about if I asked you to factor 8a cubed plus 1. All right, so again, we would look for a GCF, but there isn't one. And especially since one of the terms is 1, so we know only a 1 can go into that evenly. But it might, it's a binomial, it's 2 terms, and it's a sum. So remember, sum of squares doesn't factor. So the only hope we have of factoring would be if it's a sum of cubes, the blue one, a to the third plus b to the third. 8 is a perfect cube, so that's good. So that means that we can think of the first term as 2a to the third power. And 1 is also a perfect cube. In fact, 1 can be thought of as any power. So this does fit the pattern of a sum of cubes. And so in our formula for our a, we were going to use 2a, and for our b, we're going to use 1. Okay? So how does a sum of cubes factor? Write down the formula. Each time you write it, you'll remember it a little better. So a cubed plus b cubed is a plus b times a squared minus ab plus b squared. All right, now we're everywhere our pattern is fulfilled when a is 2a and b is 1. So everywhere we have an a in the formula, we're going to put a 2a, and everywhere we have a b, we're going to put a 1. So that's going to give us 2a plus 1. Now we have a squared, so 2a squared is going to be, if you square 2a, you get 4a squared, minus 2a for the a and 1 for the b. So 2a times 1 is just 2a. And then b squared, so 1 squared is just 1. And that's it. We know that trinomial there is going to be a prime polynomial. We can't factor it any further. All right. That's it for this lesson. So hopefully you are feeling a little bit more comfortable factoring binomials using special factoring formulas. And so when you see these in ALEKS, you'll be able to factor them. I hope you found this chat or video, if you're watching the recorded version, helpful. If you did, please remember to give it a thumbs up, give it a like, so other students can find the video. So I'm going to log off now. Goodbye, everybody. Give me a few days to get the bonus points posted in D2L. And please remember to look in our D2L classroom in the syllabus and in the announcements because there are some assignments that will help you prepare for the upcoming midterm. Okay, so thank you guys for attending the live chat, and I will see you all either Monday or Tuesday. Bye-bye.